Gwen Shapira. I'm super happy to be here with you at Monster Scale. And I'm here to talk about scaling multi-tenant applications on Postgres. So I'm going to start by talking about why scaling on relational databases is still a very hard problem. Then I'm going to talk about the properties of multi-tenant workloads and how they contain the key to solving this hard problem and effectively scaling relational databases. And then I'm going to switch and talk about Nile architecture. We basically re-engineered Postgres and used extensions and other cool things in order to create a Postgres that scales effectively for large multi-tenant applications. And we're going to talk about how we built it, the architecture, the components, how we use them, some workflows, and some examples. So let's get started. Okay, so what are those multi-tenant applications that I'm talking about? They're not exactly niche. You probably know them. They're also known under the term SaaS or B2B, essentially any application deployed in the cloud and using the same software stack to serve very large number of customers. So I put in some examples that I'm sure you're familiar with some of them. And because they are so common and they're everywhere and they've been everywhere for decades now, it is kind of surprising how difficult scaling them is. And it's that it's still considered basically an unsolved engineering problem, something that people, whenever every application reaches a certain scale, they talk about how they re-architected it, charted this, charted that, changed things. And there is no one agreed approach. It's like every one of those systems, scaling it is its own special snowflake engineering project and has been that way for a very long time. So this is a bit puzzling, right? Why is it so hard to scale those systems? And here's a place to start. It is not the application. Those applications are typically stateless. They scale very well. You put them on Kubernetes, you have a load balancer on top, you basically put it on some auto-scale rule, and they will scale fantastically. This is not a problem. Now, as they scale fantastically, usually all those application servers that we're scaling fantastically are hammering a single poor Postgres database that at some point starts to crumble under the load. And scaling this Postgres is actually the hard part. And why is that the hard part? It's the hard part because it's a relational database. As everyone who ever used or even heard of ScyllaDB knows, scaling NoSQL, non-relational data is, I wouldn't say easy. The engineering work that went into it is impressive, but I would say it's a solved problem. If you don't know how to scale your key value store at this point, it's a you issue. It is not a general engineering problem. On the other hand, relational databases, there are actually very few examples of systems that scale successfully. I can say that Vitesse is one such famous example, but there are very few of them, much fewer than there are for other types of data. And it's because scaling relational data is freaking hard. So we'll talk a bit about that before we start talking about the solution. So one way to scale, we all know there are two ways to scale, right? You scale up by getting bigger machines, you scale out by getting more machines. What happens when you try to scale Postgres up? Well, first of all, we're talking about what you scale it up on. When you talk about bigger machine, what kinds of machines are we talking about? And I would say today, most systems are deployed in the cloud. So we're really talking about larger and larger VMs. They have specific sizes, and at some point they stop. Now, today, those are pretty capable. You can get large VMs out of the cloud vendors. So maybe this is not a problem. The storage, on the other hand, even though we all know that having SSDs attached to a machine is the more faster storage option, in the cloud it's actually unadvisable. stuff happens to machines there, and it happens to their attached storage as well. So you really want to use EBS. Now, EBS and its equivalents on other clouds are actually really good as far as network storage goes. During my career, I used, all the NetApps of the world and all those similar systems. And it turns out that cloud vendors do a very good job on the storage side, but it's still network storage. It still does not have the same consistent low latencies that those relational databases were really designed to have. Now, what happens when you increase the load on one of those systems? Well, one thing that happens is the usual stuff that happens when you increase load on any system. They will use more CPU, they will need more memory, they will hammer the storage with more IOPS, which in some cases makes them actually quite a bit more expensive. And if you have combination of a lot of very small specific OLTP style queries and then few large scans, you can start having a mess made of your memory. This is not unique to Postgres. This is a general problem of datasets running, or databases running higher loads. Postgres itself has few more issues. It has a write-ahead log architecture. Writing to the write-ahead log is synchronous, which makes it very latency sensitive. Again, cloud storage actually doesn't give very good, reliably low latency guarantees. So this is a common problem. Postgres uses multi-version concurrency, meaning that as transactions come and go, you may have more than one version of every row. There is a vacuum process to clean up the versions that are no longer needed. It can take up a lot of resources. It can be noticeable when it runs. This is one of the more common problems when people run high-scale. Postgres is that the vacuum is either too disruptive, or they cannot run it often enough, or it doesn't ever complete running. And there's a whole host of problems that come from not running enough vacuums as your system scales. Postgres also has process per connection model. Process per connection essentially makes every connection higher overhead. So you want to limit the number of connections, or you'll start the overhead from all those connections will start eating into the rest of your resources. The buffer cache has known issues with scaling to very large sizes. So even though you can get pretty large high memory machines out of your cloud vendor, you will often find that you cannot effectively use all of the memory. For Postgres, at some point, just managing the LRU has its own overhead. And of course, as a relational database, contention and locks, as we're trying to maintain ACID properties and isolation with all those transactions, is also a concern. So the key takeaway here is that at some point, you can no longer scale up Postgres. Even though you can get more and more hardware, you will start running into write-ahead log issues, vacuum issues, cache inefficiency issues. You'll probably want at some point to stop scaling up and start scaling out. So how does scaling out go, really? Well, the thing with relational databases, and I know it sounds obvious, is that they are relational. The data is related to each other. And every query will touch a lot of these separate bits of data and try to put them together into a cohesive result. Now, if you distribute queries some ways, it means that every query will need to touch multiple machines, depending on exactly where the data is, which adds latency. Now, network delays between two machines in the same zone, this is not high latency. We're talking about a millisecond here, a millisecond there. So does it actually matter that we're taking a millisecond here, a millisecond there? Turns out that it absolutely does matter for three important reasons. A, Postgres protocol does not natively support pipelining, which means that you run a query, you get a result, you run a query, you get a result. Those milliseconds basically add up. If you use an ORM, and my data tells me that 60% of you statistically use an ORM, it may be a lot chattier than you'd want. You think you're writing something that could be a single query. It probably could be a single query, but you're using an ORM, so it is going to be 2 queries, 3, 10, 50. The n+1 problem is a very well-known issue in that scenario. So you are going to run a bunch of queries, latency will add up, and here's a way to make things even worse. If you remember something from queuing theory in your university days, and everyone who does performance, which all of us are into performance, we have to remember queuing theory. Performance is 100% queuing theory. You'll remember Little law. Little law is the basic law of queuing theory, and it says the number of people in a store in any given amount of time is a function of how fast people go into the store and how long they stay in the store. Yes, it sounds obvious. How does it apply to databases? Well, imagine that people in the store are queries. Time they spend in the store, that's latency of each query. And the rate at which they get into the store, this is throughput. This is usually a business requirement. You have to handle that many users, queries per second. Which means that if latency goes up a bit and we want to maintain the same throughput, we need to allow for more customers in the store at the same time. Which means in database terms that you have to allow more connections. Connections in Postgres use non-trivial amount of resources. So you can imagine going into this loop where latency goes up a bit. Now, in order to maintain throughput, you need more connections. Connections use resources, which means that latency goes up by another bit. Oh no, throughput goes down. We now need more connections. And basically everything goes into this horrible death spiral of more connections, more latency, more connections, more latency, until your entire database falls apart. Not good. Few milliseconds matter. So how is it all related to multi-tenant workloads? Let's go back and let me explain what I mean by multi-tenant workloads, and you'll see exactly how the multi-tenant workloads save the day. So this is not a multi-tenant workload. This is a normal HR application. It has a table with employees running for a single customer. 2 ways to make it multi-tenant. One is to basically keep adding either schemas or databases, one for each customer. So we have the database for customer 1, customer 2, customer 3. It's really nice, highly isolated, very secure. You can tune every customer, but you now have to actually manage all those databases and tune everything for every customer. Every operation that has to touch all those customers is going to take a long time and be complicated. There is also obviously high overhead for maintaining sufficient resources for every one of those customers, making sure they can spike, just Postgres overhead, etc. So it's the expensive and bespoke way of running things. The way most people run things is they actually shove all those customers into one schema. They add a tenant ID column on every table, and they run all those customers on a shared database. Security is now basically up to the application. One customer that gets really large can have a lot of impact on everyone else. You can never really restore data for just one customer. But on the other hand, this is cheaper and more manageable and what most people do. Okay, so let's say that we have the cheaper, more manageable options that most people use, and we look at a typical query. What you'll usually see is something like where tenant ID equals 1, 2, 3. And you'll see, if you try sampling the query, you'll see it in over 90% of the queries. They will have this where tenant ID equals. Why? Because most of the time, the way we run queries is someone logged into the app, he's part of some tenant, and he's doing some work. Everything that he does only touches data for that specific tenant. Someone else touches data for a different tenant. So this is a big insight here. Even though we have possibly a gigantic database, every query only touches the subset of the data for one tenant. How is that useful? if we isolate the data for every tenant, and we call it virtual tenant database, it's basically having separate storage and separate memory blocks and disk blocks for every one of the tenants, not necessarily separate compute. And we make sure that all the data for each tenant is on a single physical machine. This means that 90% of the queries, even though we may run a lot of databases and have a large distributed system, all those queries are local. They have a performance of touching a single machine, which is the lowest latency we can get. It's actually a bit lower because they only touch the pages in memory and in storage that belong to that specific tenant. So it's even smaller than a normally sharded system that has many tenants on the same shard. So this allows us to scale to any number of tenants, and it allows us to keep on adding nodes without adding more latency, because every query, or at least vast majority of the queries, will only touch a single node. It also means that we get security and privacy as part of it, because we enforce that any query only touches a single node. And then we have a bunch of other benefits that we get from that I'll get to at the end. So this is the key thing. We want to have the benefits of a large distributed system in order to scale and to manage it as if it's one large distributed system. But we get amazing performance benefits by separating the storage and memory of each tenant and making sure every query only operates on data on one machine. So let's take a look at how we did it in general. So as I mentioned earlier, we have the virtual tenant databases. So you as a developer connect to a database, and it looks like a normal Postgres. We call it a logical database. Behind the scenes, you actually have the virtual tenant databases, and they could be distributed on a lot of Postgres instances. If we go a layer down, the way this all works is that we have a routing layer. This is the Nile gateway. And this is responsible for directing queries into the correct tenant database. It does a bit more than that, but that's the gist. And then we have the computes. Tenants are assigned to specific compute. All their data is in the memory of that specific compute. The CPU that processes them is there, so it's all very local. This is backed by a storage service. It's based on SlateDB. There is going to be another talk about SlateDB in this conference, so I'm not going to talk too much about that. And so we have the data in SlateDB. It's backed by S3, and we also have a bunch of metadata and schemas that we manage for the entire cluster. So this is kind of the overview of what our architecture is like. So how does it actually work? Well, let's say that you want to create a tenant. This is fairly straightforward. You do insert into tenants. It goes to the gateway, which intercepts this query and handles tenant placement based on either what you told us you want or loads on different machines. We'll find the machine for that tenant and we'll create it over there. If you run a query for that tenant, you're going to tell us upfront, hey, I'm going to run a bunch of queries for this tenant. The routing layer will redirect you to the right machine. And all the queries, you don't have to have work conditions, basically, because we know that you're only interested in data for that tenant. We'll make sure that we are limiting what you do. And it's performant because you're only touching data for that tenant. And it's also safe because no matter what you put in the work conditions, you can only see data for that specific tenant. Now, let's say that you don't want to actually tell us which tenant. You want to use your old queries that you're used to. You actually are okay with all those work conditions. Well, a router can also parse your query, get the tenant ID out of that query, and route it correctly. What is the benefit of us doing it? We make sure that you don't mix tenants in a transaction. So if you do begin transaction, select from to-dos where this tenant ID, and then you do an insert, we're going to tell you, hey, you selected from this tenant, but you're inserted into the other tenant. Which tenant database do you actually want to use here? So we give you this kind of protection. Now, if you actually want to select from everyone, don't tell us what tenant you're accessing, just select from everyone. We will route you into a list loaded node, and then through Postgres foreign data wrappers, we will distribute the query. So this is a real distributed query. It is going to be slower, but we're going to assume you're not going to make too many of those. If you are planning on the majority of your workload to look like that, you probably shouldn't be using Nile. If you don't have a Nile-shaped workload, which is more heavily tenant-specific. But if you have an occasional report you need to run, this is fine. It will just be a bit slower since it's distributed. Now, what if you want to move tenant? Moving tenant is a really key part of how the system is elastic and performant, because basically either you know something about this specific tenant and you're like, oh, I want to give it more resources, let me move it proactively to a different, bigger machine. Or Nile detects, hey, this tenant is really noisy, it's starting to cause some performance problems for others, let's move it to its own machine. One way or another, it's important for a healthy serverless system to be able to move tenants around. So how do we do it? We use elements that already exist in Postgres. So we freeze the tenant, meaning we force Postgres to dump everything related to that tenant to disk, including the state of its ongoing transactions, a bunch of IDs, obviously any in-memory data, everything is pushed into disk. And then we do detach. Detach is another Postgres term. It basically says, take this partition away from the table. So every Postgres table has a partition for a tenant. We're like, okay, this partition for the tenant, it's no longer part of that table, meaning for all intents and purposes, this tenant is now offline. Step 2, we go to the other machine and notice that we did not copy a single byte because the data is still on the page service which both machines can talk to. So the other machine starts reading data for that tenant. It doesn't have to read all of it. It can just read some stuff that is related to some transactions that are currently ongoing, a bit of metadata, some IDs. It doesn't have, if the customer has a terabyte of data, it can still only read a few kilobytes. It does not have to touch all of it. So this is very fast. And then we do unfreezing, which mainly means updating a bunch of IDs of transactions so they will make sense on the new machine. You don't want to have collisions between ongoing transactions and transactions that already finished and all those IDs. So we do this update, and now this tenant is visible and we can resume routing queries into the new machine. This is completely transparent to anyone using it. Cool. So we've shown you how our architecture provides with tenant isolation. The tenant data is separated in storage and in memory. How we give you elastic tenant placement, and we can even move tenants around to resolve performance issues and balance load. This architecture also gives a lot of other non-performance related capabilities. We can track the usage and performance of every tenant individually. How much are they actually costing you? We can do point-in-time recovery for one tenant because we have separate storage for each tenant. We can branch specific tenants if we want to run some tests on how will this feature impact this tenant. So a lot of cool stuff we can do here. This is definitely a case where one simple trick and one simple architecture just keeps giving a lot of really nice benefits. So to sum things up, scaling Postgres scales really well up to a certain machine size, and then it starts becoming extremely challenging. Luckily, multi-tenant applications can be sharded by the tenant key and separated into those either real tenant databases or virtual tenant databases, which are a lot easier to manage since they're part of one cluster. They still share the same schema, and you have flexibility around how they use the compute. And by separating compute and storage, we can really distribute those isolated tenants across a cluster and have a very efficient management and performance for this type of workload. So the other key takeaways is that the solution to any performance problem is find ways to reduce latency and find ways to chop the workload in a smart way so you can distribute the workload without having to actually increase latency because you have to touch a lot of machines. If you have this way that turns the problem into ridiculously parallelizable, then you've basically won. So I hope you enjoyed the talk, learned something new, and possibly became more interested in Postgres as a result.